Harlech Castle sits on the west coast of Wales, overlooking the Irish Sea. It was built in 1289 by Edward I, King of England, and despite several battles, it remains in good condition.
But the reason we're here today has a lot more to do with the castle's geography than its history. This is the Watergate, and the steps I've just come down are called the Way from the Sea. That's because ships used to be able to sail right in here to deliver goods to the garrison based in the castle. That was 800 years ago, but the situation is a little different today.
Harlech Castle now stands over half a kilometre from the sea. It's all due to the processes that are changing the coast. To understand what's happening, we need to start at the southwestern corner of Wales, in Pembrokeshire. This is one of the most exposed parts of the Welsh coast because the prevailing winds are from the southwest. Waves driven across the Atlantic smash against the cliffs, continually wearing them away.
The harder pieces of coastline, like this headland, only erode quite slowly. But the softer bits, like that bay, get eroded much more quickly. And it's this difference between hard and soft rocks that leads to the repeating pattern of bays and headlands.
Although these cliffs are all made of the same material, Carboniferous limestone, the rock isn't uniform throughout. It has weak layers, faults and cracks running through it, all prime sites for erosion.
The erosion is due to several processes. There's hydraulic action, where the crashing waves compress water and air trapped in cracks, weakening and eventually loosening the rock. There's abrasive action, where material suspended in the water gets smashed up against the cliff face. And finally, there's chemical action, where the rock is dissolved by seawater and the rain. And just below where I'm standing is an absolutely stunning example of all these processes at work. This is the Green Bridge of Wales, a fabulous example of a sea arch.
If we go back 5 million years, the coast would have looked like this. First, the sea goes for the weak bands of rock. Then it goes for the cracks in the harder rock, forming first arches and then stacks. This leaves the Green Bridge as we know it today. It's easy to guess what will happen in the future. Not all stacks are formed this way. Sometimes they just get left behind as the coastline around them erodes.
Those stacks will get worn down by the waves and the weather and become stumps, like this one.
Arches and stacks aren't the only structures carved out by the erosion on these cliffs. Here, waves have punched a hole in the bottom of the cliff, and then the erosion has opened up a vertical fault, like a chimney, forming this huge blowhole. The bays left in these limestone cliffs are relatively small. When rock types of differing strengths are placed together, the bays can be much bigger. St Bride's Bay is a good example. It's 15 kilometres from one headland to the other, and it's all down to a difference in rock type. The northern headland of the bay is made up of hard igneous rock. The southern headland is a mixture of igneous rock and sandstone, which is also pretty hard. But in the middle of the bay, the rocks are mostly sedimentary rocks, which are much weaker than the rocks in the headlands. Over several thousand years, the softer rocks have eroded much faster than the harder rocks, forming St Bride's Bay. The sea isn't the only force that erodes the coast. This cliff is made up of an Ice Age deposit of sand and clay. And in places, the top sandy layer seems to have slid down on top of the clay. It's been caused by rainfall, and the process is known as cliff slumping. The sand layer is permeable, but the clay layer isn't. When it rains, the water soaks through the top material, but it just collects in the clay below. As the base of the cliff gets waterlogged, it becomes unstable and collapses. Eventually, the debris on the beach is swept away by the sea, leaving the cliff exposed once more. So far, we've only considered erosional processes, but what happens to all the broken-off pieces? To find out, we have to head north, back towards Harlech.
And here it is. All that stuff that was knocked off the cliffs to the south of me has been ground down by the sea and washed up here as sand and pebbles to form a beach.
Borth Beach, just north of Aberystwyth, is about 2 kilometres long. The sand is on the lower part of the beach, and big waves throw the pebbles up to the top of the beach. But how does it all get here in the first place? The answer is longshore drift. The process depends on waves hitting the beach at an angle, as they do along much of this coast. Let's concentrate on just a few particles. The particles are washed up on the beach by the waves, which, driven by the prevailing wind, hit the beach at an angle. As the water runs back into the sea, it pulls the particles straight back down the beach under the force of gravity. The next wave moves the particles a little bit further up the beach, and so on. The process is known as longshore drift. Even in small waves, you can actually see sand particles in the water. This movement of material means that over time, beaches can change their shape and sometimes disappear completely.
That's why people build these groins. These wooden partitions trap material on the beach and prevent it from being carried away.
At Borth, nearly 60 groins have been built to ensure the beach isn't taken away by longshore drift, but they don't stop the movement of material completely. Inevitably, pebbles and sand get swept over or round the groin and continue their journey. And this continued movement creates another feature common to this stretch of the coastline, spits. Spits are formed where the line of the coast changes, but the longshore drift carries material on. A river estuary is a good example. Longshore drift carries material along a straight line out into the sea. When enough material has been deposited, a spit forms. And there are several examples along this part of the coast.
These dunes mark out Harlech Spit. They've built up because so much material has ended up here. There's not just one line of dunes, but several, stretching all the way to the end of the spit, nearly 6 kilometres that way. The spit itself is massive, almost completely cutting off the river estuary behind it.
The reason for this accumulation is the change in the direction of shoreline north of the spit. There, the Llane Peninsula sticks out 50 kilometres to the west, acting like an enormous groin, halting the onward movement of material. Over the course of nearly 1,000 years, the area has changed enormously. Originally, the castle would have been on the coast. Then longshore drift and deposition has created a spit across the estuary mouth. Material trapped behind the spit has formed a marsh. Saltwater-tolerant plants have grown, trapping more sediment, and the area has turned from marsh into land.
Today, the castle is high and dry, nearly a kilometre away from the sea. In between are sand dunes, a golf course, houses and a caravan park. If he were alive today, King Edward I, the guy who had the castle built, would not believe his eyes.
The Kaiteriti Spit, a nearly 30-kilometre-long deposit of cobbles and shingle, is one of the most fascinating landforms on New Zealand's coastline. The story of how the spit came about is tightly bound up with the story of many other landforms in the region. The formation of the spit is, in fact, the last of many events that, together, have produced the look of the landscape as it is today. To cover these events, the best thing to do is a lightning tour of the area's physical geography and squeeze quite a few millions of years into a matter of minutes.
The lightning tour starts right here, where one of a number of extinct volcanoes meet the sea. And it'll also finish right here, in just about 2 minutes' time.
100 million years ago, no spit, no plains, no volcanoes, no mountains. Then, 26 million years ago, two plates collided and the New Zealand Alps were thrust up. Another plate movement caused lots of earthquakes and the volcanoes sprouted. 2 million years ago, the temperature dropped and New Zealand got its ice age. 12,000 years ago, the ice melted and left behind thick deposits of drift that became the plains and the coast itself.
A coastline made of glacial drift, absolutely typical of much of New Zealand's South Island, and eroding, as you can see, pretty fast. But that's not the end of the lightning tour. There's another process going on here that completes the picture: longshore drift.
As always with longshore drift, material eroded from the cliffs gets transported along the coast in the direction of wave attack. If there's a bend in the coast, the material carries on, forming a spit, the Kaiteriti Spit.
The spit has now grown to a total length of 26 kilometres, and at this spot we're almost at that distance from its root, back there. And the last 500 metres of the spit run straight into the old volcanoes, where we started the tour.
The spit is a perfect reminder of a crucial fact about physical geography. Although it often doesn't look like it, landforms are always changing and on the move. Rocks actually travel. Those on the Kaiteriti Spit are mainly a rock with the strange name of Greywacke, exactly the same rock from which the New Zealand Alps were formed. It's interesting to imagine what kind of a journey a single lump of Greywacke might have made.
It could have been shaken off the top of a mountain by an earthquake, then brought down in a landslide, then carried down the mountain in a glacier, then picked up by a river and brought to the sea, then transported by longshore drift from 100 kilometres back there. It's a very New Zealand story.